Suppose that we have a measurable discrete random variable y with range Ry, and we have an integral random variable, because it doesn't have to be discrete, x, and they are living on the same probability space omega fp. Now the question is, show that the conditional expected value of x given y is measurable with respect to the sigma field generated by y. And the definition here on the right, this is just the definition of the conditional expected value of x given y. Now, when we need to show that the random variable is measurable, the first thing we should be looking at is to see whether the random variable is perhaps discrete, because if it is discrete, then the test of measurability is technically much easier. So what do we have here? We have the sum. Now this sum is over all the values in the range of y. Now we know y is a discrete random variable, so this range is going to be finite or perhaps countable. Is over all values of x in the range of y, so that the probability that y takes x is bigger than 0. Now this condition is a technical condition. It is simply there to make sure that this value can be calculated, because of course remember that the expected value of x conditional on y equals x is by definition equal to the expected value of x times the indicator of this event divided by the probability that y is equal to x. So of course if this is 0, then this is undefined, so this is why we can only add up over the values for which this probability is positive. So what we have here is we have the sum over these quantities. They are numbers. You can see it's an expectation divided by a probability. This is a number, and multiplied by the indicator function. And of course this is a conditional expectation, is a random variable. It's a function of scenarios, so if it's a function of omega here, the only place where omega enters into this equation is as the parameter of the indicator function there. So what you can see here is you have a random variable that takes countably many different values, and it takes each of these values on a set, and that set y equals x is exactly an element of the partition of y. So one thing we can say for certain is that on each member of the partition of y, this conditional expectation x conditional on y is constant. And what I mean by that is, in other words, if x is in the range of y, then we have expected value x given y applied to omega. Now if you imagine that omega is in the event y equals x, then if we plug such an omega into this equation, then you'll find that the indicator function is 0 for all the other x's, except for this one x. It will be 1, and the value that it will pick up there is expected value of x conditional on y equals x. So clearly this is a number, and it's the same for all omega on this element of the partition. So one thing that we can certainly say is that this conditional expectation must only takes one value for each different value of y. So it takes countably, or maybe even finitely, many different values. So the conditional expectation of x given y is a discrete. It's a discrete random variable. Moreover, if we think about the partition of this random variable, then this partition can't be finer than the partition of y. The reason for that is that it's constant on each element of the partition of y. And remember, the partition of y is exactly the elements of the partition are exactly those sets on which y itself is constant. So the partition expected value Ex given y is not finer than the partition of y. Okay, so this is what we can see by just writing down the definition. Let's have a look and see what the question is asking. The question is asking you to show that this random variable is measurable with respect to the sigma field y. Now, the sigma field y is the smallest sigma field that such that y is measurable with respect to this sigma field. We also know it's the smallest sigma field that contains all the elements of the partition of y. So that is interesting. In fact, I've just realized I was a little bit imprecise in my final statement here. I think we need to be more precise here. The partition of y is finer than the partition of expected value of x given y. The reason why I say that is that it can be that for different values of x, if you compute this ratio, by coincidence it could be the same. So it could be that on two different intervals corresponding to two different x, this conditional expectation is actually the same. So it can be that the partition of this random variable is actually different from the partition of y, but certainly we can always write a member of the partition of this random variable as the union of members of the partition of y. Now, the reason why this is important is because, remember, sigma of y is smallest sigma field containing members of the partition of y. Now, if it contains a member of the partition of y, if it contains two members of the partition of y, it will also contain all the countable unions of those, because of course it is a sigma field. So, in other words, sigma y smallest sigma field containing countable unions of members of the partition of y. But this is exactly what we were saying here. The partition of y is finer than the partition of expected value of x given y. We know that if we say one partition is finer than the other, it means that the less fine partition, in other words the partition of y, all the members of this partition can be written as as finite unions or countable unions perhaps of members of the finer partition. In other words, sigma y contains all members of partition of expected value of x given y, and this exactly means that expected value of x given y is sigma y measurable. And there we go. Thank you.